Welcome to today's Explainer. I'm super excited to guide you through this because we're looking at something that is literally all around us, yet completely invisible. We're going to demystify the M2M eUICC, specifically zooming in on the GSMA SGP.02 architecture. If you've ever wondered about the hidden infrastructure that keeps millions of connected devices talking to each other without any human intervention, well, you're in the exact right place. Okay, let's just think about this for a second. Imagine you're a utility company. You've deployed 1 million smart meters across an entire country. Now imagine your network operator contract expires and you've got to switch providers. In the old days, that meant rolling out trucks and sending human technicians to physically swap out 1 million tiny plastic SIM cards. I mean, it's a total logistical nightmare, right? The cost and the time involved make it practically impossible. So let's dive into this and see exactly how modern engineering solved this massive physical dilemma. Here's our roadmap for today. 1. The M2M SIM problem. 2. Core architectural entities. 3. The over-the-air journey. And 4. Waking up the machine. Starting off with Section 1, the M2M SIM problem. Enter SGP.02. This is basically the ultimate blueprint. SGP.02 is the official GSMA remote provisioning architecture, and it's designed specifically for the embedded UICC, what we call the eUICC, in machine-to-machine use cases. This standard is the rulebook. It's what allows network operators and businesses to securely beam a brand new network identity straight into a device, whether that's a smart meter on a house, a sensor deep inside a factory, or a shipping container moving across the ocean. Moving right along to Section 2, Core Architectural Entities. Now, to make this remote provisioning magic actually happen, we need to meet our cast of characters. First up is the destination of our journey, the eUIC. Unlike the traditional plastic SIM card you can just pop out of your phone, the eUIC is an embedded secure element. It's soldered directly onto the circuit board of the device itself. You can think of it as an impenetrable secure vault inside the machine. And instead of holding just one network identity, this vault is capable of housing multiple network profiles securely. So what exactly goes inside that vault? The profile. The crucial point here is that a profile isn't just some simple password. It's a highly sensitive, operator-specific digital package. It contains the mobile network operator's credentials, an entire file system, specific applications, and something called the Network Access Application, or NAA. This profile is essentially the digital soul of the network connection, and it needs to travel securely to our vault. To get that profile securely into the eUIC vault, we use two incredible pieces of infrastructure. And this brilliantly illustrates the division of labor in the GSMA standard. On the one hand, we have the SMDP, or Subscription Manager Data Preparation. Think of this as a highly secure packaging facility. It prepares, encrypts, and binds the profile specifically for the target eUIC. On the other hand is the SMSR, or Subscription Manager Secure Routing. If the SMDP is the packaging facility, the SMSR is the armored delivery truck. It never looks inside the package. Instead, its sole job is to manage the secure over-the-air communication and lifecycle operations, things like enabling or deleting a profile directly with the eUIC. Of course, beaming the keys to a network over the air requires, well, extreme paranoia. The intense cryptographic reality making all of this safe relies on PKI-based mutual authentication. That means the servers and the embedded chip mathematically prove their identities to each other before they even think about talking. They use elliptic curve key agreement to generate keys on the fly, and PSK-AES secure channels based on global platform standards to encrypt the data. And the whole shebang is anchored by a certificate issuer. That's a root of trust guaranteeing absolute trust between every single entity. Literally, no one gets to participate without a verified certificate. Let's move on to Section 3, the over-the-air journey. So the package travels on a highly secure, invisible highway built on standard protocols. The transport layer utilizes secure channel protocols, specifically SCP-80 or SCP-81. What's super fascinating here is just how flexible this is. The data can be pushed over something as simple as a hidden SMS, or can use HTTPS for faster data transfer via the bearer-independent protocol, regardless of the route. The profile itself is sent as a sequence of APDU commands, entirely wrapped up in those unbreakable secure packets we were just talking about. It's basically a highly coordinated relay race from end to end. Step 1 begins with the network operator triggering a request to the SMDP to create a profile. In Step 2, the SMDP creates it and encrypts it using the specific public key of the destination eUICC. This means absolutely only that exact chip can open it. For step 3, our armored truck, the SMSR, establishes the secure over-the-air session with the eUICC. And finally, step 4. The profile is downloaded, installed, and successfully enabled, either replacing or living alongside an existing profile in that vault. And that brings us to section 4, waking up the machine. So, the digital package has successfully landed and the vault is closed. But our story isn't over yet, because at this exact moment, the machine itself is still totally asleep to its new identity. The moment the profile is enabled, an internal chain reaction kicks off inside the device. First, the eUIC sends a profile enable notification back through the SMSR so the operator's backend knows the operation actually worked. The next step is a big one, the baseband refresh. The eUIC literally sends a command to the device's baseband processor, forcing it to clear its memory and reread the file system. It's essentially telling the machine's cellular brain to wake up and look at its new identity files. Then, the network access application initializes, finally exposing the new IMSI, which is the subscriber identity, and the highly secret authentication keys to the baseband. Let's move ahead and see how this builds. Armed with its new identity, the newly awakened device performs PLMN selection, which basically means it starts scanning the airwaves for its new home network. Once it finds the right radio cell, it initiates an RRC connections setup. From there, it boldly sends an attach request directly to the cellular network's core, whether that happens to be a 5G, LTE, or legacy 2G or 3G network. This triggers a split-second rapid-fire handshake, because the network doesn't just let anyone in, right? It issues a cryptographic challenge, sending a random number and an authentication token directly to the device. The device passes this challenge straight down into the eUICC vault. Inside, the network access application uses some pretty intense algorithms, like mileage or TUOC, alongside its secret key to compute a very specific response. And then it fires that response right back to the network. If the math checks out, boom, mutual authentication completes. In the background, session keys for encrypting voice and data are instantly derived. Deep in the core network, the subscriber database updates the device's physical location. And finally, the packet data network connectivity is activated. The data pipe is officially open for business. And there we have it. The SIM is fully functional. The device now has full voice, data, and SMS service. If there happens to be a screen on this machine, the user interface will actually pull the operator name directly from the newly active profile and display it. We have totally changed the physical identity of this machine without ever sending a truck, without opening a plastic cover, and without ever touching a circuit board. It's truly a marvel of modern telecommunications. Just think about the sheer scale of this. As you go about your day, pass by utility meters, drive near connected cars, or walk past smart city sensors. I'll leave you with this question. How many millions of invisible, encrypted handshakes are happening all around you right now? Thanks for joining me on this explainer. I hope it completely changed how you look at the connected world. Keep learning, and I'll catch you on the next one.